We will discuss a numerical on Macaulay method. Here say a beam, simply supported beam AB subjected to a point load of 20 kN and a UDL of intensity 10 kN per meter, right? And initial conditions are given, value of modulus of elasticity for this beam material and moment of inertia about the cross section of beam is given. This is 20 into 10 to the power minus 6 meter to the power 4. Now what we have to calculate? We have to calculate deflection at C. At this point we have to calculate the deflection, then maximum deflection of beam where it will deflect maximum, and slope at end A, right? At end A we have to calculate slope, right? Now what we do, first we will establish a bending equation, a bending moment equation, that is EI d2y dx2 equal to, we say it a Macaulay bending moment equation, right? Here it is equal to mx, and this will be equal to, get a section, make a section here in between the segment CED, right? And say distance of this section from end A is x, right? Then take moment of all the loads about this section, then it will be RA into x, then there will come Macaulay bracket after first term. Macaulay bracket is this one minus 20 into distance will be x minus 1, right? Next is 10 into 2, right? 20 kilonewton will be total load. 10 into 2, 20 kilonewton will be total load of this UDL, right? But if we see, we have to take the UDL of this length only, right? And this length will be equal to x minus 2, right? This distance is equal to x minus 2. Then total load of x minus 2 length of UDL will be 10 into x minus 2. 10 into x minus 2, right? It will be 10 into x minus 2. So distance is 10 into load minus 10 into x minus 2 is total load, right? It is total load. Clear? Now we will take the moment. The moment, the 10 into x minus 2 is total load acting in downward direction, and we have to take the moment of this downward load about this section. Then sectional distance of this load is x minus 2 by 2, right? Then we will multiply by x minus 2 by 2 into this equation, right? Now for this is the requirement for deflection of beam, that we must know the how to calculate reaction at the supports of the beam, right? So this is, say this is 20 kilonewton, right? Here from end A 1 meter, right? And now what we see, 10 into 2 is 20 kilonewton acting at a distance of 1 meter from this end B, right? So what we finding, that both 20 kilonewton is acting in downward direction and they are equidistant from their supports A and B. So reaction will be equal to RA plus and RB, RA equal to RB will be equal to 20 plus 20 by 2, right? That means each 20 kilonewton will be supported by these supports, right? Why? Because magnitude of these point load is same and they are equidistant from their supports, right? Meanwhile there is no load, so we can say that that's this total half of this total summation of load is shared by each support. Then half of this total summation will be 20 plus 20, 40 by 2, right? Then 40 by 2, 20 will be supported by this and 20 will be supported by this one. Then RA equal to RB will be 20. So equation will be, now here equation will be 20 into x, and there will be Macaulay bracket Now minus 20 into x minus 1 minus, and this will be equal to 10 into x minus 2 square by 2, right? So this is the governing equation, Macaulay governing equation for this method. Now we will calculate slope, we will generate equation for slope and deflection, right, through this equation. Now we have equation, this is our equation, final equation, right? See it and write equation for slope. Integrate this term one time, then what we will find, ei dy dx equal to, it will be 20 x square by 2 plus c1, and here will be Macaulay bracket, right, minus 20 into x minus 1 square by 2, and this will be equal to minus 10 x minus 2 cube upon 6, right, x minus cube upon 6. This is the equation for slope, and integrate it one more time, then equation will be ei into y, right, 20 x cube upon 6 plus c1x plus c2, and here it will be minus 20 x minus 1 cube upon 6 minus 10 x minus 2 cube upon 18, right? It will be 3 plus 1, then it will be equal to 24. 24, 5, 1, 12, right? So this is the equation, this is the governing equation. Now we will put boundary condition for the calculation of deflection at C and for the calculation of deflection at maximum deflection, right? Now if we put the boundary condition that, okay, say at end points we know here at this point, right, at this point if we make a deflection of this beam, then the beam will be deflected like this way, right? It will be deflected like this way, clear? Then at this point there is no deflection, because deflection is start from this point. So for x equal to 0, y is 0. For x equal to L, that is the length of beam, that is x equal to 4, y is 0. Put these two conditions for simply supported beam, right? Here for x equal to 0, y equal to 0, then from this equation what will happen? From this equation what will happen? When we put x equal to 0, then C2 will be equal to 0, right? C2 will be 0. Now for x equal to 4, length of beam is 4, we know that y is 0 at another end, right? Here at this end y is 0 and length of beam for this is 4, x is 4, right? Now put this value, then what will be the answer? We will calculate it, y is 0, then we will find, put this here, then it will be 0 equal to 20 into 4 cube upon 6, right, and plus c1 into 4, and all these term will be 0. Why? Because it is a singular function, there is no need to put, right, there is no need to put the value, this is x equal to 4, right? We are taking value of x is 4, then we have to put all value here in this equation, because we are considering whole length, then each load is participating, then it will be C2 is 0, then there is no need to mention it, right? And open this bracket, then if we put finding this value, then bracket will when bracket will be open, then answer will be, this will be minus 20 by 6 4 minus 1 cube minus 10 upon 24, and this will be 4 minus 2 cube, right? When we simplify, then what we find that C1 is coming, C1 is equal to minus 29.16, right? And so what is C2? C2 is 0. C1 is 29.16 and C2 is 0, right? For simply supported beam, deflection is 0 at the supports point. When x is 0, y is 0, right? These two equation will, when the x is 0, right, then only first these two term will be considered, right? First these two term will be considered. There will be no participation of these load, so they will not be mentioned, because this is a method of similarity function, and they are similar function, they will be 0, right? Because these functions are valid when x is greater than 1, and this function is valid when x is greater than 2, right? Here in this term, when x equal to 4 and y equal to 0, why each terms are participating? Because we already said that this term will participate when x is greater than 1, here x is 4. This term will participate when x is greater than 2, then here x is 4. So they are participating, and finally value is C1 equal to minus 29.16. Now, what will be modified equation? Modified equation is, right, put the value of C1, C2, then modified equation is EI dy dx equal to 20 x square by 2 plus C1 is it is minus 29.16, right? Minus 29.16 plus Macaulay bracket minus 20 x minus 1 square by 2 minus 10 x minus 2 cube by 6, right? X minus 2 cube by 6. Now here this is x minus 1 and this will be x minus 4, right? This will be x minus 4, do mention, because it is cube, x minus 2 cube, then it will be x minus 2 to the power 4, right? Now what will be the deflection equation? Deflection equation will be EI y 20 x cube upon 6 minus 29.16 x, C2 is 0, and here in bracket minus 20 x minus 1 cube upon 6 and minus 10 x minus 2 to the power 4 upon 24, right? These are the two governing equation, and with the help of these two equations we will calculate deflection at C. Now what we have to calculate? We have to calculate deflection at C, right? That is y at C. Deflection at C, first point, right? So we know that for point C, here in the beam loading diagram, point C, x is equal to 2. We have to calculate deflection at this point. So at this point, x is equal to 1 plus 1, 2, right? So for y at C, x is equal to 2. Put this value into deflection equation. Then what we will find? We will find EI into y 20 into 2 cube upon 6 minus 29.16 into 2, right? Minus 29.16 into 2 minus 20 into 2 minus 1 cube upon 6. we will not put the value of this x equal to 2 into this term, right? Yes, there is no need to put the value of x into this term. Why? Because this term is valued when x is greater than 2. This is a singular function, right? So this is the property of singular function, that this term will exist when x is greater than 2. But here x is 2, right? And this is existing because x is 2 and x is greater than 1, right? So this is the equation, right equation. Now simplify it and put the value of ei into this equation. So when we will simplify, we will find that this is yc will be equal to minus 34.98 upon, put this value ei, and ei is given. When we will simplify, then value will be minus 8.74 mm. This will be our answer, right? So get the simplification and find the value. Minus sign indicating that deflection is measured on negative y-axis, right? It is measured at negative y-axis. So how we will mention it? This is the C point, right? Then deflection is at this point. Deflection is yc, and it is equal to 8.74 mm. 8.74 mm. Right? Now, next is we are required to calculate maximum deflection value, right? Maximum deflection. That is calculation for y max. We have to calculate y max. We know that deflection will be maximum when slope is 0, right? When slope is 0. And here, from this figure, right, we have to judge it by hit and trial, and we will solve a number of problems through a number of examples. Then we will be able to judge by looking to the problem that this is saying that the maximum deflection will happen in between C and D, right? In between C and D. Say we are assuming that deflection is happening, maximum deflection is happening in between C and D. Clear? So when we will consider C and D, then only two terms will be involved, right? Because only two terms will be involved, because when x will be greater than 2, right? When x will be greater than 2, then this term will be involved, right? But for x is greater, when x is greater, for C and D, x is greater than 1, right? Then load for bending moment for this one and bending moment for this one will be involved in analysis, right? So y max, say it is happening between maximum y max is in between C and D point, right? We're assuming it. Then we know that for maximum deflection slope is 0. dy by dx क्या होता है? dy by dx is 0 for maximum deflection, right? For y max, dy by dx is 0. Now put this equation. Put the equation of deflection 0, and deflection equation that we have established is 20 x square by 2 minus 20 9.16 minus 20 x minus 1 square by 2 equal to 0, right? When we put it in 0, then value of x coming is from this solution of this equation. The value of x will come solid. When we will solve it, then value of x will be 1.958 mm. 1.958 mm. Right? This is the value of x. Clear? Now, for at this value, we will calculate the maximum deflection. Right? What we finding that At x equal to 2, deflection at C was 8.74, right? And for the value of x less than 2, there is happening maximum deflection. Let's find out the value, right? Then value at this point will be EI y max. Put this value into deflection equation. EI y max 20 into 1.958 cube upon 6, right? Minus 29.16 into 1.958 minus 20 into 1.958 minus 1 cube upon 6, right? When we'll solve it, then value will be minus, right? Y max will come minus 35 upon EI. Put the value of EI here, then value will come 8.75 minus 8.75 mm. This is Y max, right? And YC, what at YC value was 8.73, 8.74. So this is larger, this is greater than by which amount? 0.01, right? So our assumption is right that Y max is taking place in between C and D. Clear? And we know that in simply supported beam, generally maximum deflection occurs at the center of the beam, right? Now we have to calculate third point. Third point is slope at A. We have to calculate the value of slope at A, right? Then slope at A, right? So for slope at A, x is 0. Put the value of x into deflection equation, slope equation. Then value will be EI dy upon dx equal to 20x square upon 2, term will be 0, that is 20, x is 0, that is 0 square by 2, and minus 29.16, right? And another term will not happen because x is, that functions are valid when x is greater than 1. So this term will be 0, this term will be 0. So dy by dx is here, if we say it, this is our theta A, so dy by dx equal to minus 29.16 upon EI. When we will simplify it, the value will come minus 0.00729. 0.00729, right? Now change it into a degree because this value is in radian. This value have come in radian. Then theta A will be minus 0.00729 multiplied by 180 upon pi. Then value will come in degree. Then this is minus 0.417 degree. Why it is negative, right? Let's understand it. What we have done, this is our beam, right? A, here is load D, here is point C, right? Beam is deflection, like there is the deflection this way. Here at this point, deflection is maximum, right? This is the Y max at distance 1 point. X is for maximum deflection, X is, right? We have calculated it. .958 mm deflection is maximum, and this is point C. At this point deflection is yc is equal to 8.74 and y max is equal to 8.75, right? And this is at 2, right? Now we have calculated the slope, right? Slope is measured. Here we will draw a tangent. This is our tangent, and this angle is, we have calculated, this angle will come, right? This angle is 0.417 degree. 0.417 degree. At end A, it is calculated. This is 0.41, and why it is minus? Because it is measured in clockwise direction. It is measured in clockwise direction, so this value is negative, and this is equal to 0.417 degree, right? So this is the calculation that we have done, right? Now we will discuss another method for calculation of deflection, right? This method is known as moment area method, and this is suitable for the beam subjected to, right? This is suitable for beam subjected to single load, right? Subjected to single load. By Morse theorem, a derivation is explained. It is not the part of your syllabus, right? So by Morse theorem, it has been established for moment area method that maximum slope will be equal to A upon EI, where A will be area of bending moment diagram. Area of bending moment diagram. And maximum deflection will be equal to A upon EI into X bar, where X bar is the location of centroid, from reference axis, location of centroid of BMD from reference axis, right? From reference axis, right? These are the two governing equations, and with the help of these two formulas, we will calculate the value of maximum slope and maximum deflection, right, through moment area method. Suppose here is our cantilever beam, right? Our cantilever beam subjected to a point load at this end of magnitude W, right? Then when we will draw, and length of beam is from this point is L, we will draw the bending moment diagram for this. The bending moment diagram will come like this way. Here value will be W into L, right? This is a right angle triangle, and if we calculate, so this is point A and this is point B, right? When we will calculate value of maximum deflection and maximum slope, then we know that cantilever beam bend like, say this is the initial point, the initial line, it will bend like this way, right? This is known as elastic curve. In first lecture we have explained it, we have understood it, elastic curve, and this is the neutral layer line. This is point A. Then here will be slope maximum, right? If we draw a tangent at this point, this is our tangent, then this will be theta A, and theta A is theta max, and here is maximum deflection. At this point is y is max. So we have to calculate this value with the help of this bending moment diagram, right? With this bending moment diagram, this is point A. Then we know that theta max is equal to A upon EI. Then area will be half base is L, this length is L, base is L, and height is WL, right? WL upon EI. Then this will be equal to WL square upon 2EI, This is theta max. Now, second thing is y max. We have to calculate y max for this one. Y max is equal to A upon EI into x bar. We have calculated A upon EI. This one is equal to A upon EI is equal to WL square upon 2EI, and x bar is equal to, this is the centroid. This is the centroid, and distance of this centroid from reference axis is 2L by 3. 2L by 3. So multiply it by 2L by 3. Then what will be the value of y max? Y max will come W L cube upon 3EI, right? Because 2 and 2 will be cancelled out. Then this is WL cube upon 3EI. Then this is the value for y max, and this is the value for maximum slope by through moment area method. So this is suitable for cantilever beam subjected to point load, right? A single point load. So whenever there is a single load on the beam, then you should prefer moment area method. And when there is more than one load on the beam, then you should go for Macaulay method.